Welcome to the Barracuda Application Model webinar series. This installment will be focusing on the direct reduced iron shaft furnace application model. My name is Neeraj Mehta and I'll be your host. With me is Tanner Stelmach. Thank you all for attending. I'll start by giving a brief intro to CPFD software, our product, and our webinars, and then I'll turn it over for Tanner for detailed discussion of the application model. In today's webinar, we will be discussing, as I mentioned, the DRI shaft furnace. The webinar is being recorded and playback will be available later today. For those of you who are attended or registered, if you join halfway through or anything, you will get a link to the recording and it will be emailed to you. For past webinars, you can go to our website where you will see previous episodes in this series, as well as webinars we've done through the years, both hosted by ourselves and with our partners, and live talks from our users conferences and other events. During the webinar, questions are highly encouraged. On the GoToWebinar panel, there is a questions tab. Feel free to ask any questions that you may think of, and we have set aside time at the end of the webinar for a Q&A session. If you come with a question during the webinar, ask it, and it'll be answered at the end. So if it comes to your mind, don't hesitate. And with that, I will start by giving an introduction to CPFD software for those of you unfamiliar with us. So this is the team at CPFD software. I think you can actually spot Tanner and I in the back row there. Here at CPFD, we're advancing multi-phase simulation technology. Our flagship software, Barracuda Virtual Reactor, simulates the physics, heat transfer, and chemical reactions in industrial scale units. While the plurality of our usage is for fluidized beds and other fluidization systems, we work broadly with any commercial scale fluid particle systems. Barracuda has been used by engineers and researchers across a variety of industries in every phase of the development, deployment, maintenance, upgrade, retrofit process. This includes design, scale up, troubleshooting, optimization, and even patent application. Our flagship software is Barracuda Virtual Reactor, which is a physics-based engineering software package that, like I said before, simulates the heat transfer, chemistry, particle physics, and fluid dynamics in industrial scale systems. When we consider dense particulate matter, fully bidirectionally coupled physics, heat transfer, and chemistry, and industrial scale calculations that can resolve in a practical timescale, there's really no other software in the market that checks all the boxes. There are software packages that model particle interactions at high resolution, such as DEM tools, and there are CFD codes that can capture dilute particulate flow by abstracting it against fluid dynamics calculations. But in many systems, simulating both phases with high fidelity is critical. And as such, Barracuda models continuous Eulerian fluid and discrete Lagrangian particles, coupling them tightly and resolving them simultaneously. I'll get more into the unique features of the software shortly. The software is a full software package, including a preprocessor and a post-processor, which is the bundled visualization tool TechBot for Barracuda, an industry standard for visualizing fluid dynamics simulations. The software can be run on Windows or Linux, largely run on local hardware, but we've seen an increasing shift towards cloud-based calculations and cloud instancing. And also, very critically, the software is parallelized by NVIDIA GPUs, which has unlocked massive speed boosts that have allowed for these simulations to resolve in practical timescales. Barracuda is divided into two broad domains, gas fluid domain and liquid fluid domain. The first broad domain of the software is gas fluid domain. So Barracuda simulates bidirectionally coupled particle physics and fluid dynamics. The particles displace the fluid and the fluid acts on the particles via drag. And additionally, Barracuda models truly multi-phase heat transfer and multi-phase chemistry, where solids and fluids can both be created and destroyed through reactions. Fully user-defined reaction kinetics and drag models are possible, as well as full user definition of material properties. The software allows for unlimited materials in the fluid phase and unlimited particle classes, each with their own drag models, physical properties, material compositions, and particle size distributions. Historically, gas fluid domain was the primary use of the software, And in recent times, we've expanded to liquid fluid domain, which has increased the capacity for applications including VLS systems. This was released a couple years back after many years of development, and it marks a massive expansion in the domain of the software. Same as for gas fluid, there are coupled hydrodynamics, heat transfer, and chemistry with user definitions for all materials, kinetics, and drag models. And again, there are there's an allowance for unlimited materials in the fluid phase, as well as unlimited particle species, each with their own drag models, physical properties, material compositions, and particle size distributions. Um, there's the capacity for discrete bubbles for gas in the system, and these bubbles can coalesce and break up, and they likewise can interact chemically with all phases. And now to talk about our application models. This is something our staff has been working on for the last year and change. And these application models serve as models that anyone online can right now, or any active licensee can download and run today. They're, for example, for people who have just completed training, people are often wondering how to get started. And so these models can serve as starting points for making your own models in terms of basic parameters and configurations. But these models are valuable for new and old users alike. They show how a paper or real system is translated into the software. Importantly, again, you can download them and run them today. Everyone on the call could go pick one up right now and run it and be able to visualize and post-process shortly thereafter. And not only can they be downloaded and run, they can be customized. In Tanner's talk, he will highlight how the models can be modified to provide further insight beyond what we've given to you. So with that, I will be handing it off to Tanner. Since joining the team in 2023, Tanner Stelmach has worked as a CFD engineer. He's worked on commercial projects. He's contributed to the support and training teams, and he's supported the development of Barracuda Virtual Reactor. Additionally, he's been working on creating these application models that we've been illustrating for you in this series. Tanner received his bachelor's in chemical engineering from the University of Colorado, and we've loved having him on the team. So Tanner, if you're ready, I'll hand it off to you.
All right, thank you, Neeraj, and thanks to everybody for making the time to come out and listen to our webinar. We're excited to share this work that we've been doing on developing this application model for direct reduced iron shaft furnace for steel production. Before I begin, just want to confirm my screen is sharing.
Yep, we can see and we can hear.
Okay, great. All right, without further ado, let's go ahead and get started. All right, so I want to lay out a quick agenda for this talk. I'll be talking about what is direct reduced iron steel production and how does it fit within the broader steel production industry. I'll talk about why Barracuda is a suitable tool for modeling this type of process in three-dimensional domain. We'll showcase our application model that's available on the CPFD website and give a demonstration of how it might be used in a manner that can be useful to you. And we'll talk about how this application model can be extended onto further iterations of this model, including the operation of a hydrogen-based shaft furnace. Right, so currently, the steel production industry is a very emissions-intensive industry. That's because the dominant technology is blast furnace basic oxygen furnace technology. This accounts for about a 68% share of global steel production. And that technology is very coal dependent. So in recent years, a lot of focus has shifted towards direct reduced iron. This technology is growing. It's expected to grow up to 24% by the year 2030. So how does it work? Direct reduced iron steel production is the process of converting iron ore or hematite into direct reduced iron using what is called a shaft furnace. In that shaft furnace, these iron ore pellets flow in through the top. They interact countercurrently with a reducing gas where they undergo reduction. That reducing gas is primarily composed of a mixture of hydrogen and carbon monoxide. And typically that comes from the catalytic reforming of natural gas. That's what is described in these units over here. So those solids, as they undergo reduction, they travel through this moving bed. They're transported down here into what is called the cooling zone. And in that cooling zone, they interact with a gas rich in methane that is fed in here, where they continue to travel and they're extracted here from the bottom as the final product. All right, so you can imagine for a system like this, you have a moving bed, you have a complex network of chemical reactions, you have heat transfer, and all of these things are intertwined and linked. And so being able to understand this phenomena inside the shaft furnace in three-dimensional space is very complex, but it's also very useful because we can take a look inside, we can understand how changing key operating conditions can impact the internal dynamics and the performance of this system. So there are a number of models that are available in literature for direct reduced iron shaft furnace. These all provide their own insights. They are one-dimensional in this case, two-dimensional, or they assume axisymmetry. So these do provide insight into operation of this system, but really in this model, we build upon this work, extending this work into a three-dimensional domain. This is really where, this is a high value point for Barracuda because we can take existing literature, existing kinetics from literature and apply them to this three-dimensional domain. Here we have the full shaft furnace process looking at the solids distribution. In that process, the iron ore or hematite is converted into magnetite, then to woostite, and then to iron. So you can really see sort of the progress of the reduction in this shaft furnace. One thing you'll notice is this is a very large industrial system, and we run it over this very long transient time scale. So this is something that's possible in Barracuda thanks to GPU acceleration and a lot of work that has gone into the code to make it, make this process very efficient for modeling. All right, without further ado, I want to get into the actual setup of this application model. So these operating conditions and geometry are sourced from a plant currently operating up in Quebec, Canada. These plant data are provided in H₂-DRI 2018 paper. Essentially, the system is for a compressible flow with particles. We have, as I mentioned, this feed of iron ore that comes from the top. It undergoes reduction. This is where the reducing gas inlet, where that reducing gas comes in. The reduction progresses here. The solids are transported and they interact with cooling gas here in the cooling zone. That cooling gas is fed in through the bottom flow boundary condition here. And the majority of that gas is removed through this gas vent, about 90%, whereas only about 10% of that methane makes it up into the reducing zones. So you can imagine for a process like this, you have relatively slow motion of solids. You're going to have a high residence time for this type of system. And so we want to come up with an initial condition that gets us to a steady state as quick as possible. So that's why we initialize a solid distribution at the beginning of the initialization here. We expect this shaft furnace to develop a solids distribution based on these stages. So we have the hematite here, and then as the reduction progresses in the shaft furnace, we'll have these solids distribution develop over time. The idea here is we want to get to a steady state more rapidly. And so we begin with an initial distribution. All right, so talking about reaction kinetics here, one of Barracuda's capabilities is really modeling discrete particle reaction kinetics. And what that means is modeling the kinetics of an individual particle or pellet. And so for this particular application, we use the unreacted shrinking core model from literature. This comes from a paper back in 1976 by H₂-DRI. In that paper, they described two different pathways for the reduction of iron ore. That includes one by hydrogen and one by carbon monoxide. For this particular shaft furnace, that reducing gas contains a pretty even split between the hydrogen and carbon monoxide. It's about 50% hydrogen and 32% carbon monoxide. You will notice that for this reduction by carbon monoxide route, it does produce CO2. And so we'll talk about some some operating conditions that we are modifying in order to preferentially undergo reduction by hydrogen and therefore mitigate some of these emissions of CO2. That is, I'll talk about that later in this presentation. But this is the current setup for Barracuda's chemistry. All right, I've shown an example of how these discrete particle reaction rates are configured in Barracuda. So we have a very intuitive user-defined expression editor here. So in that, you can reference all the variables that are available in Barracuda. This is available from this drop-down list here. And we can really enter these expressions based on information and data that we have in literature for these reaction kinetics. In addition to these discrete particle reaction kinetics for iron ore reduction, there were a few more that we included. We have carburization reactions, these two, which are reactions 7 and 8, where in which carbon is deposited onto these particles. We also have the production of iron carbide, which is another key component in steel. And then we have two different volume average reactions here. These are homogeneous reactions. The difference being for volume average reactions, these reaction rates are resolved on a cell-based level rather than on an individual particle-based level. So this is very useful for these homogeneous reactions. All right, and so I want to share some results from our investigations here. We have a comparison of the solids mass fraction for a plane, the ZY plane here. We compare it with a two-dimensional model in literature reported in Hamade paper, and we do see some similarities. One thing to note here is that the Hamade paper does assume axisymmetry, and so we do see very nice symmetric profiles here. Our model does not assume that, and so you do have some diffusion and dispersion of solids here in the reducing section. But one characteristic that is observed across both of these cases is sort of this preferential motion of solids through the center of the shaft furnace. So we see that for these intermediate species like magnetite and woostite, those travel preferentially through the center. And we'll talk about how that is also observed with it's consistent with some of the temperature profile results that we've looked at as well. But we do see similarity between our results and those in literature. All right, then I want to talk about how this connects with Barracuda's modeling of heat transfer in this system. So Barracuda does capture heat transfer between the particle and fluid phase. It also does capture the endothermic reduction reactions here. So we have this reducing gas, which is fed in through the inlet here. That is a higher temperature, about roughly 1,000 degrees Celsius. That gas interacts with the solids, where it undergoes endothermic reduction by hydrogen. And so you see in the center here where these solids are traveling that there is a cooling zone that evolves here in the center. So we do see lower temperatures in that region. One thing to also note here is this system has very low particle velocity, very low difference between the fluid and particle velocity, and so you don't see a significant in the fluid and particle profiles here. All right, then I want to talk about this this gas distribution. So in our model, we see once again a lot of similarities between our work and those described in literature. We have in the reducing gas inlet a higher concentration of these hydrogen carbon monoxide species. As the reduction progresses, that produces both water and CO2, and so you get those products evolving here in the upper section of the reducing zone. And then we see for the methane, which is primarily confined to the cooling zone, that comes from the cooling gas from the bottom. Only about 10% of it makes it up. And so we see this sort of narrow stream that comes in through the reaction zone. So a lot of these dynamics are consistent with this work. So that's kind of an inter-model comparison showing how our model maps against literature, but we actually want to see how it tracks against available plant data. So this same plant that's operating out of Canada, we went ahead and compared our results with the outlet gas composition from that shaft furnace, and we do see a lot of consistency between our results and those in that that plant data. So a lot of similarity there, and a lot of this provides confidence that our kinetics are accurately describing the dynamics in this system. I want to point out here that for this system, once again, this is a very large industrial system. It has to be run for a long period of time in order to reach a steady state, about 5,000 seconds, which is about 1.4 hours of real time. So this is possible thanks to a lot of work that has gone into GPU acceleration with Barracuda. So thanks to that work, this model takes about 5 days to run. So this is something that can be run, and in a period in less than a week, results can be analyzed and used for analysis. All right, so that being said, I want to go ahead and give a demo of where this application model can be accessed and how you would go about using it for your own application. So just want to confirm, is my browser visible here on the screen?
Yes, we can see your browser.
Okay. All right, so under the CPFD website, we have this resource, and there is a section here for application models. So we'll go ahead and open that. This was also featured in Niraj's presentation, but we have an entire library of application models that have been developed by our engineering team. So these include kinetics and correlations that have been validated in literature, and they describe very detailed demonstrations of how these kinetics and geometry were implemented in Barracuda. We'll go to this direct reduced iron shaft furnace example that we're looking at here. This directs you to a preview page that describes sort of a quick summary of what this application model is about. We want to actually go into this Access Model button, which will direct us to the more detailed description of the model. All right, so within this application model, we have a lot of the content of this presentation is outlined in more detail. In this model, we have a description of how DRI fits within the broader steel production industry, description of this process. We describe all of our geometry, operating conditions, and sort of the description of how this system works, our solids initialization. We then go and describe in detail reaction kinetics, including the unreacted shrinking core model that we discussed. All right, so continuing on here we describe, for this case, our results, how that maps against different models available in literature. And then alignment with plant data here. We just describe our solids distribution. And then here's where you can actually go ahead and get started with downloading and being able to use this application model for your purposes. I'll come back to this. I want to direct your attention first to a lower section where we show how to go through some of the post-processing. So CPFD does have a big library of tech plot tutorials that are really useful for being able to generate visualization, generate nice contour plots. So those animations and images that I showed in this presentation, how to generate them is detailed in this section here. And then we have references here at the bottom. We'll go back up to the modeling instructions section. And here we have all of the support files, the project files that are that were used to generate this project. So I'll open that. This can be downloaded as a single zip file. Contains all the necessary files to start running your application model. You do need to have a support site account in order to access these materials. So if you'd like to start running this model and start using it, this is something that we're happy to come talk to you about and get you set up with a support site account. So I'll show you, this can be downloaded directly here. For this purpose, I have a GUI session already open and available here. And so this is a project that has been run out for some time. I'll show, basic setup here. We have all of our solid species. This is the, these are the solids that were initialized in the bed. This is where we initialize our solids distribution. And so you can see we define different regions where those particles are initialized within the domain. Then we get into our boundary condition setup. So this boundary condition is for the reducing gas inlet. And so one thing I'm going to talk about in this presentation is how changing the reducing gas composition can be done. And so that comes in through this section. We can actually modify composition here. This was the reducing gas composition from the Midrex natural gas-based process. And so, as we mentioned, it's about 50% hydrogen and 30% carbon monoxide. So if you did want to adapt this to a hydrogen shaft furnace, this would be with a much higher concentration of that hydrogen. And then we'll also talk about how we tested over a design space of various temperature and pressure conditions for this process, which are available in this flow boundary condition editor. All right, then I want to go and actually go in and demo some of these user-defined reaction kinetics. So this was the one that was shown in this presentation where we described the reaction of an individual particle. This is the unreacted shrinking core model. And using all the variables that are available in the Barracuda GUI, we can actually compute a reaction rate coefficient for each time step using those variables. Here we have our reactions, full set of reactions, including the volume average for those homogeneous reactions, as well as our discrete reactions here. All right, then I want to show, another feature we discussed is this GPU parallelization. So if this is something that you have available, we definitely recommend using it. This can drastically speed up the runtime of these simulations. And so you go ahead and select that and go ahead and run the solver. This one has already run. So we're going to go ahead and do a quick demo of actually generating and viewing some of these results in Barracuda. I'll go ahead and go to view results to open up a tech plot session. One moment. All right, so this is a tech plot window that contains a visualization of particles in the system. This is a particle volume fraction view. For the final runtime, this is that 5,000 seconds. So we want to generate a quick visualization of the solids distribution that we outlined. So in that support file package, we do have layout files that are included. I'll show how to open those. These are just available in that directory. And so go ahead and select open layout. Then there is 2 layout files. We'll go to solids distribution first, open that. Then we'll go ahead and replace the current layout without saving that. This is just this layout currently in view is just the default particle volume fraction view, so discard that. All right, and here we have the full distribution, the motion of solids of hematite to magnetite, woostite, and iron over time, as well as the temperature profile for the fluid and particle phase. And so, we do have, once again, more detailed instructions on how to generate these views on the application model post. But if you just want to generate results very quickly, these layout files can be very useful. So we recommend just opening them and viewing the results that way. I'll go ahead and show the same for this gas distribution. So we'll go here to Open Layout and select Gas Distribution. All right, and here we have the full suite of mole fraction profiles for the shaft furnace here. And instructions for generating this view are also available once again on that post. So this is a description of how you would actually go about running the model and visualizing and generating some results. And the idea here is that based on the application model instructions, it should give you everything you need to get started running the model. And we also do have a support team who's available if you have any questions as you're getting started using the model. But moving on to our next section, I want to talk about how these application models can be downloaded and they can actually be adapted in order to extend this work to different iterations of the current geometry or the current design. And so one change is actually operating with what's called a hydrogen-based shaft furnace system. This involves replacing a lot of that carbon monoxide in the reducing gas feed in order to mitigate some of those CO2 emissions. So before I get into that, I want to talk about our collaboration with Molten Industries on this work. We're working with Dr. Kevin Bush, who's been instrumental in helping us with this work. Dr. Kevin Bush is the CEO and co-founder of Molten Industries. And this company is at the forefront of something really exciting. They are developing a process to produce clean hydrogen and synthetic graphite using only electricity and natural gas. The idea being this is something that is profoundly useful in the lithium-ion battery industry. The process significantly reduces CO2 emissions and is able to produce graphite at low cost. But one of the co-products of this process is clean hydrogen at low cost. And so we see a lot of decarbonization potential in downstream sectors like steel, chemical, and energy sectors. And so in collaboration with Molten, we've been looking at adapting the system to operation as a hydrogen-based shaft furnace. We talked about in our base model operation of DRI with natural gas-based process. This gives us about 50% reduction compared to conventional technology of blast furnace, basic oxygen furnace technology. However, further replacement of that reducing gas feed with hydrogen can get us up to around a 90% reduction, according to mid-rex data. So this is something that really can be leveraged in order to lower emissions in this industry. And so this collaboration comes in. Molten has developed this patented pyrolysis technology that produces clean hydrogen. This is something that we are adapting to be used with this type of shaft furnace process. All right, so taking the setup from the original mid-rex natural gas-based model, we want to replace a lot of that feed with higher concentration hydrogen. But you can imagine hydrogen is a much lighter gas than this CO hydrogen blend. So there's going to be some trade-offs here. We see that these do affect the hydrodynamics and the heat transfer quite a bit. And so some considerations in the actual system design were made when setting up this model. One of those was operating the system at a higher pressure. The idea being here that if we operate at a higher pressure of 7 bar, this will increase the residence time of this system. And it also increases the partial pressure of our reactants in this reducing zone, drives the conversion of these solids more rapidly. So in order to do this model setup, we wanted to come up with a model setup that was as close to hydrodynamically as the operation of this Midrex natural gas-based model. So we start off with a flow rate and temperature that is equivalent in terms of the Reynolds number of flow coming in through the reducing gas stream. And that comes to about 4.8 kilograms per second of reducing gas coming in here. This view shows slices in the z-plane of the volume fraction of solids in the shaft furnace over time. So you can see here there is more, similar to what we observed in the Midrex case, there is preferential motion of these solids through the center of the vessel. These solids travel down and kind of they kind of travel through the center of this bed as they undergo the reduction. But I do want to point out, comparing our current modeling results with this hydrogen-based shaft furnace, we do see a lot of potential in terms of the ability of this process to significantly reduce emissions compared to base case. So we see about a 97% reduction. We also see that that doesn't come at the cost of performance for this type of system. So we see that there's only about a 1% reduction in metallization, which refers to the purity of the iron product being withdrawn from the bottom of this shaft furnace. So Barracuda is really good at running over a number of different design matrices, running a number of tests and comparing results over those different conditions. So basically what we want to look at here is how we optimize the cost of this process, reduce the for operating a system like this while still maintaining performance for the system. And so ultimately operating at a lower temperature, lower flow rate is going to equate to cost savings. And so we tested over a design space ranging from 700 to 1,000 Celsius and 3.5 to 4.8 kilograms per second for that reducing gas. So this testing is currently ongoing. It's something we're working with our collaborators on continuing to test and understand. But what we do have some trends that we are currently observing here. One is that we see that changes in the flow rate, like reducing the flow rate of the reducing gas coming in, results in a higher degree of channeling of these unreduced solids in the bed. So those magnetite solids, which are an intermediate species, we don't want to see them come out and basically cause impurities in the iron product being removed here. So reducing that flow rate does contribute to a drop in the performance. We also see the same as observed for this, for lowering the temperature. So what we see here is that lower temperatures contribute to a higher degree of channeling of these solids as well. This trend is impacted by the kinetics. So lower temperatures mean lower reaction rates. And so more unconverted solids making it down. For this flow rate case, we see that at lower flow rates, there is a lower gas penetration. And so the actual amount of reducing gas cannot actually go in and break up these channels and result in full conversion in the center. And so there are a few things that we're looking at currently to try to mitigate some of these channeling effects. One is to actually use baffles that would help to break up these solid channels in the center of the bed and like cause dispersion of the solids before they make it into the cooling zone. Another would be to operate at the right combination of this temperature and flow rate condition. Right, and I wanted to quickly show for this system, in order to adapt the model we currently have on this application model post to operation as a shaft furnace, you could come here to this system and we can make adjustments to the actual composition. So for those tests, we use 100% hydrogen. This mixture mole fraction can be changed to 1. And you can also make changes to temperature for this reducing gas inlet as well as the flow rate. All right, coming back here. Right, and with that, we have some references here for all of the kinetics in the data that was used for this. And I'd also like to acknowledge collaborators for this process. We worked closely with the Molten team. Dr. Kevin Bush was very helpful in this process, as well as Dr. Shashank Kara and Dr. Jim Parker from CPFD. I'll turn it back over to you, Neeraj.
Thank you, Tanner, for your presentation. Okay. And then I'll let him get a quick breather before we get into the Q&A session. In the meantime, I'm going to go over our offerings. Please use this time to ask questions using the side panel. So for those of you interested in trying Barracuda who are not currently customers, there's a few ways that you can interact with CPFD software and collaborate with us. Primarily, Barracuda Virtual Reactor is delivered via software licensing. So you would purchase a annual license for the software, and this license will allow your engineers to use Barracuda Virtual Reactor. Of course, you still have access to our world-class support teams. But again, this is the primary way people use our software, but it's not the only way that people work with us. We also have an engineering services team, largely project-based, but as a small company, we are always adaptable and flexible for working with different forms of collaboration. This includes for licensing and services, and for even things in between. For example, our Quick Start program, where our staff engineers set up the first model in the software and deliver it to your team. So we'll take input data, we'll take geometries and operating conditions and parameters, set up the first model, and then deliver that model to your engineers along with the license. From there, you can use it as you see fit. We have regular new user training classes held online, about 6 to 8 sessions per year. But also we offer custom training if you want to have several members of your team trained at once, or a site training. We are amenable for that. Like I said before, we are a small team, so we're always looking to fit the solution to your team's needs and your timeline and your budget. And then beyond that, we also work with a large swath of not quite customers, not quite clients, not quite researchers. These are our partners, and these range from research consortiums to technology developers and software providers, cloud computing instancing providers. So again, if you're interested in working with us, please reach out to us at info@cpfd-software.com. Reach out to Tanner, reach out to myself, and I'm happy to continue the conversation. I just wanted to give a quick highlight to upcoming events for CPFD software. Like I said before, we have training classes. We have one at the end of this month, and I believe we do have some seats available in the class. So for those of you who are not yet customers who are watching this webinar and interested in trying the software, please reach out. We'd love to enroll you in the class so you can get a feel for the software. The class is fully online, meets for an hour a day over the course of a week. We provide a week-long license as well as cloud instancing, so you don't have to have anything. You can just show up and be able to run the software. Again, we also have a class at the end of April. CPFD will also be attending the Society of Petroleum Engineers Gulf Coast Section's CFD Group's annual symposium. We have I mentioned on the previous slide, our partners. One of our partners is PSRI, a research consortium based out of Chicago. We are longtime members of PSRI. They host a fluidization seminar that's held all around the world. It's been in Switzerland, it's been in Texas in the last year or so. We give an invited guest lecture on one of the days of the seminar. For those of you who are looking to brush up on fluidization basics, um, there's no better source of information in town than the experts at PSRI. So they have a talk in Chicago in April as well as in Daejeon, Korea in March. And then immediately following the seminar in March, CPFD is hosting alongside our Korean distributors KBT Solution an emerging fluidization applications workshop. So it's be held in the same hotel the day after. If you are already attending PSRI, we highly recommend that you stick around an extra day and attend the workshop. The workshop will feature talks from our staff engineers. We'll be covering not only this application model, but some of the other ones that we've created, as well as some latest research that our staff engineers been working on. It'll feature talks from PSRI, from some of the big corporations in Korea, as well as Korean academia. So um, highly recommend if you are in Korea that you swing by. Our next application model webinar has been scheduled for April. This will be a cement calciner. We have a few different cement application models published or in development right now. This will be the first in that set. Please register. For those of you who are on this webinar, we will be, the follow-up email will have a registration link. And then also, be sure to follow us on LinkedIn. You will get all these updates, as they happen. It's probably the best way to keep up to date with everything on us. That and checking our website. And then finally, last but not least, our users conference, which is held every other year, is coming back to Chicago this year. Details to come with regards to who's speaking and other events, but the users conference is set up and ready to go. Highly recommend that everyone attend this. It's not just for experienced users of the software. We have people from every level of expertise, from industries ranging from materials and chemicals to petrochemicals to power generation and a lot more. We have people coming from all over the world. Everyone shares their latest insights, their latest developments, what they're doing with the software. And CPFD, we'll take the opportunity to share the cutting edge advancements, the new stuff in the software. So again, this Chicago, our users conference is coming back, and we hope to see you there. And with that, I think we can get into the Q&A session. So I'm going to pull up our questions panel here. Tanner, are you ready to answer questions?
I am.
Okay. Starting here, we got a question. Can the model incorporate processing of other mixed metal oxides using H2 rather than iron ore?
Yes. So in Barracuda, you can define an unlimited number of solid species. And so if you want to define an additional particle species, that can certainly be done. If you have an idea of how of what the kinetics are from literature, that can also be input. So there is a lot of flexibility in Barracuda in terms of including additional species or additional data.
Yeah, fantastic. And I think this person had a pair of follow-up questions. He said, for example, mixed metal oxides like lithium, nickel, manganese, and cobalt with the general formula of metal 1 and then oxygen 2. Sorry, I'm reading this poorly. And he said the focus here is nickel, manganese, cobalt, and excluding lithium, which will likely flash off. So I think, yeah, Tanner kind of addressed that. When you create your materials in the system, you can define them with all the material properties as you know them. And then, like Tanner said, if you have reaction kinetics either derived from literature or experimentally, you can also input those in as well. So it's not limited to iron in any way. It's really up to whatever you can provide to the system. And I do really appreciate the question. I think we'll follow up with you because I think that is a fantastic use case for the software. So we got another question here. Hello, I'm new to Barracuda. Can you please tell me how you define particle feedings? Is it continuous feedings or specific quantity? Tanner?
Yes. In Barracuda, we use what are called flow BCs. Those include a continuous particle feed, but we do have a lot of flexibility in terms of if you have a non-continuous feed. If you're pulsing in particles that might be over smaller time scales, or that feed is not steady, that's something that certainly can be implemented. Also with, the SFF editor is a great way to do that. And so we're able to use Barracuda inputs to define flow rates over certain ranges of time. I think that might address the question.
Yeah. All right, next question. Will these presentation slides be shared after the webinar? The slides themselves, no, but the presentation will be available in video format. I'll follow up afterwards. If there's specific parts of the slides that you're interested in, we can certainly send over some of the materials. So I'll make sure to follow up with you after the webinar. Just a couple more questions here because I know we're going to the hour. How can I try an application model myself? So if you are a licensee, just go to our website and download it. There's really not much in the way. You'll get a zip file like Tanner showed. You'll be able to open it up, make sure you have enough hard drive space and a good GPU, and hit run. And if you're not an active licensee of the software, talk to us. So we can set up a trial. We can get you in training. There's various ways that you can try these application models ahead of being a licensee. So yeah, reach out if you're not yet a licensee. Another question here, I think for you, Tanner. How did you initialize the solids as you say close to steady state?
Yes, so the idea is we want to, this model does have a fairly high residence time. So we want to start off with, in Barracuda, we do need to have an initial condition or an initial distribution of solids. And we have the ability to choose what that might be. We do know, however, that over time, these kind of solid stages will develop. We will have a region of where hematite exists in the shaft furnace, as well as magnetite, woostite. And so we came up with that initial condition to reach a steady state as rapidly as possible, and to reduce the amount of computing time that's required to get to a steady state.
Okay. You had mentioned, here's another question about, you had mentioned baffles inside the furnace. Can you simulate thin-walled structures and internals?
Yes, so Barracuda does have a lot of capability in terms of being able to simulate internals using baffles. So for these type of internals, usually they're very thin walls. So being able to capture them with a computational grid requires a lot of computational energy. And so baffles are useful because those exist on a subgrid level, so they don't actually need to be gridded. So what we do is we define them in the domain. We define a pass-through probability, which will tell us how much of those particles can pass through that internal. You can imagine this can vary depending on the internal. For something like a screen that might be semi-permeable, you might have some solids that make it through. For something that's just a wall, no particles will get through. And so baffles offer the ability to model these internals without having to increase the computational complexity so much due to having to capture these really small internals.
Right, yeah, I think there's generally like an upper limit to how many cells you can define, both, before you get numerical instability, and also, like you said, like practically for computation. Another question here, where to start the model process if the oxide chemistry is known, but the interreaction kinetics are not?
So can you repeat the inner chemistry?
So like the question asker, they know the oxide chemistry, but the interreaction kinetics are not known. So where would they start for modeling this?
Well, I would start by implementing the reduction kinetics as they are, and then there is some plant data that's available. It is limited because there's some of these processes can be proprietary, but I would start off with the solid kinetics and then just see how your model aligns with existing plant data or validation. So you might be seeing a significant amount of one species that's not observed in that plant data, and that would indicate the need to include more fidelity in your system, be able to model additional reactions that might be happening between species in the system.
Sure. I think we have time for a couple more questions here. Um, let's see. Here's a question. Why was the methane high compared with the plant data? Like the methane in the simulation high compared with the plant data?
So the methane, we do apply a boundary condition where we withdraw a certain amount of methane from the cooling zone. So still, about 10% is supposed to make it up. You will notice in additional models, there is sort of some dispersion of the methane and some consumption happening in the reducing zone. So we do include that chemistry. It is a little bit higher. So the idea here is, we could add in additional chemistry that could, this is sort of a base model. We could add more fidelity in to improve the modeling of the methane in the reducing zone. But our model currently does slightly over predict that. It's not a significant amount. I think it's a few percent difference. But you are correct that is slightly different with the plant data.
Okay, I think we have maybe time for one or two more questions. Here's one. Is a moving bed considered a fluidized bed? The users or the attendees asking, I thought Barracuda was for fluidized beds.
So you're correct that a moving bed is not a fluidized bed. These particles are at a close packed volume fraction, which is not a fluidized state. And so, Barracuda is very good at modeling fluidized beds, but a lot of modeling effort or engineering effort and model improvements have been made in recent years to model dense flow. And so adding in the momentum redirection model that improves the modeling of like the collisions between these particles, adding in dense collision model. And actually in our new version of Barracuda, we've included a elastic collision model, which will further improve the granularity of modeling these collisions at dense packing. And so yeah, a lot of strides have been made on that front for being able to model dense flow in Barracuda.
Fantastic. I think we have time for another question or two. I'll just field this really quickly. We have a question here about am I able to set up an H₂-DRI model using your application model? And a follow-up question of what if I have different Ferris dimensions? And I just want to wrap up here by saying application models are a great starting point, but you can modify. So if you have different feedstock, if you have different geometries, if you have different temperatures, profiles, those can all be input. So this is application models. Again, they're a great way to get started with the software, but the world is your oyster. So you can take them and modify them to suit your needs, your process, and that's exactly why we've made them for, like we said, a starting point. And I think with that, that wraps up our webinar. We're getting close to the hour here. So I would like to thank everyone for attending and for participating. And we'll see you at the next installment of our application model webinar series. Thank you.